Hey there, welcome back. This is Dave. Just wanted to give you an update on the project. I've got to a pretty solid beta version in my the teaching tool that I'm making to teach inductive power transfer or wireless power transfer or witricity, whatever you want to call it. But so I'll introduce you to the parts of it. This is the transmitting base, and it's just a black box. There's two ports back here for taking oscilloscope readings. These are directly linked to the coil. And then you have your DC input, you have a switch, and you have a status light down here. Let's go ahead and turn this on. So, totally safe to touch. It transmits, there's a primary coil inside, transmits at around 170 kilohertz. Right now, that might change. So it's transmitting kind of a bubble of magnetism. It's a big electromagnet that we're actually creating with this oscillating field. So the field is around here, and it actually goes underneath this glass table that I have it on. So I'll show you the effect of that later. The kit would come with one transmitter and probably four of these little receivers. So you can imagine that you'd have probably 4 students per lab station, so preferably 3, but these you could buy probably separately. You'd only need one base. This could be even used for demos and stuff, where you'd only need one base and one transmitter, but if you wanted to get students to take measurements, you don't want like 5 kids crowding around one receiver. So this is a receiver. The only thing that's in this is a coil and a AC to DC rectifier, couple of LEDs right there, and then on the back there's a voltage ports that are you can take voltage readings that are across the DC rectifier outlet. The output's the positive and negative. So anyway, let's give this thing a go. Let me show you real quick just how it works. Students rather would take voltage measurements, voltage versus distance measurements, which is why the ports are there. And we'll connect that here in just a little bit. So they can take voltage versus distance measurements, and they can experiment with the range of the effect. So it kind of goes out there and gets a little brighter as you get in the center. They can experiment with polarity. So this, when the alignment is perpendicular, you don't get any magnetic flux going into this coil, so you don't get any current moving. So if you don't have any current, you don't have any voltage. You can't light anything up. But the instant you move it over here, the flux is a bit bigger, but there's a hole right in the middle. It's pretty interesting. And even if you lift it up a bit, it's still not going to work. But once you turn it parallel to that flux, you begin to get current flowing again. So it even works underneath it. Well, let me get it. Sorry, let me move this away from the metal. Doesn't like metal, because metal, it causes a magnetic field. So underneath the glass plate, it also works too. Works at a fairly good distance. It's about an inch underneath it. And again, this is a beta. I want to get, I'd love to get a good solid 6 inches above and below. Right now I'm about, let's see, where are we? We're probably right about 4 inches or so, 4 or 5 inches anyway. So let's connect this to some of the meter readings. And also another experiment is not just to take distance versus voltage, but shielding. So how do you stop a signal from getting to this most effectively? Well, metal's pretty good an insulator in this example. So what I'm going to do is I'm going to put a big chunk of metal on there. It's a big 6-volt battery. And this thing definitely does not like that. So you've got magnetic field is being disturbed by that metal, and then as soon as you take away the battery, even at that same height, even higher, it works again. So unobstructed works really well. Even just a tiny bit of metal will shield this. So another interesting experiment. So you can try to make a challenge of how to shield it with the minimum amount of materials, which is what happens in your cell phone. So interesting, very real-world things you can do with this. It's a modern twist on the light bulb, the wire, and the compass, so, and the battery, so, which is kind of traditional how to teach electricity or induction in physics. So let's wire this thing up. Let's take some measurements. I'm going to try and do this with one hand. So I got some little banana clips right here, and I just kind of plug them in. Super easy. And again, doing this with one hand. So now I've got it plugged into the receiver. Still works perfectly fine, and I've got voltage measurements. So as I raise this, so you can imagine a group of students doing this, as I raise this up, you can get voltage readings. And what's interesting is that another investigation is how much voltage do you need to actually get the LEDs to light up. So I'm getting almost 1 volt, but yet I need a bit more, about 1.6 to raise it up. So, and I can get pretty far out. Where to 0? We're 0 volts, and that's a good, almost a foot above the transmitter. So pretty interesting. Take a look at the curve on that. It's definitely not linear. It's kind of an S curve, and it's a quadratic, is what I've plotted several times using this. So a little bit of math involved. You can also see the effect of the alignment. There it is. Yeah, where's that hole? So we have a little bit of voltage being passed through. I can't quite get it right. There we go. So it's down to 0.58 volts if the alignment is incorrect. So again, pretty interesting. You can also again transmit from below it and on the sides. Let's take a look at the oscilloscope. Right now I don't have it plugged into the ports. I'm going to do that for you right now. And this thing is on the whole time. So I'm going to take one port and plug it in. Oh. God, this is not easy with one hand. Okay, and then the other one. Okay, and now we have our oscilloscope plugged in. And again, thing is on the whole time. So we can see the waveform generated across the primary coil that's inside the base, and the voltage being read here. As we move this up and down, the waveform changes slightly. The amplitude gets a little bit lower, but the waveform doesn't change much. So I'm still working on getting a perfect sine wave, not quite yet. Need a little bit of tuning. So anyhow, that's the project. I think it would work fantastic in a school environment as a demo, or a teaching tool that you would give to kids in individual lab stations. Not sure about the cost right now. It's kind of a significant cost to do the prototype, but I'm hoping to get a full set, 1 transmitter, 4 receivers for less than $100. Ideally, that would be something affordable, and we'll see. Thank you very much for watching.